In this video, we're going to think about the forces on loops of current. Now, this first picture is a little bit complicated, but all we're trying to do is think about how two loops of current interact with one another. In this case, we're looking at circles for simplicity, but they really could just be rectangular loops or really any sort of loop that you want. We typically deal with either squares or circles for simplicity. Now, there's two different ways to think about it. One is poles, and the other are currents. So when we say parallel currents attract, what that means is that if you look at the top, the current's coming out of the page, and in the bottom, it's going into the page. So remember that these are cross sections through our loop. So our current is doing something like that, assuming that what we can see is actually the back of the loop, right? So assume that this is a donut where we're seeing the back of the loop. On the other hand here, we have it going in at the bottom, coming out at the top, and then we have it coming out at the bottom, going in at the top. So again, think about this in terms of parallel currents attract, opposite currents repel. Either you can think of this as clockwise or counterclockwise, or you can look specifically at what's happening here. So this is rather difficult to draw in a three-dimensional way, but you could imagine I have kind of a loop here, and I have a loop there. See, that already looks terrible. Now in this case, if what we're trying to do is look at the situation here, we know that here it's coming out and here it's coming out. So really both of these have a current going this way. So another way we would do this is, for instance, just trying to position an eyeball and really say, how are we looking at this? So in this case, they're both rotating the same way. In this case, they're rotating opposite ways. So again, attract versus repel could be something that you experimentally observe. But a second aspect of this is that we can predict that that is going to happen. So how can we do that? Well, let's go back to our wires. So long straight wires, we said that if it is parallel, they attract. So in this case, it's not a long straight wire, but each piece has a piece here below it that is parallel and the current's going in the same direction. So that's one way to think about this, that this is just like a long parallel wire in that the parallel currents attract, opposite currents repel. Another way you can think through this is the magnetic field. Now, this is a little bit tricky because we know that the magnetic field of loops makes some kind of complicated shapes. But let's try to draw the magnetic field from this left loop and understand what's happening at the right loop. So I've used my right hand rule to just sketch really basically what the magnetic field is doing around each of these. And again, we're thinking about it caused from this wire. But let's now think about what that's going to look like over here. So again, the magnetic field at this point from the loop to the left is going this way, and then here it's going that way. So do your I cross B. At the top it's coming out, and then B is up. That gives you a force to the left. Here it's going in, B is down. That also gives you a force to the left. So doing the magnetic field, and obviously here we're not thinking about every single point, we're just picking 2 points, but you know that the loop is rotationally symmetric. So we can take any point here and we can actually rotate it and the picture will look the same. So that's one way to think about the fact that this works, that every point we get a force to the left. Now, this is one way to think about it, just directly thinking about forces due to the currents and the magnetic fields. Another way is to remember our rules for the North and South Pole. So very briefly, north is where your field was coming out. So this is your north side, and so south is where your field is going in. So this picture here is identical here, but we've labeled it to be south and north. So notice that if we have south and north on the left of this one, because this one has currents going in the exact same way, you have south on the left, north on the right. North and south attract. So we see that it attracts just due to the current in the magnetic field, but if you want to use the shorthand of thinking about magnetic poles, then you get exactly the same effect. So on the bottom, I'm not going to do it out directly, but again, you can actually try to look at the magnetic field from one wire at the location of the other, and you see that this would cause forces to the right, which is then going to make these repel. We could then double check and ask what are the magnetic fields from the right wire at the left wire, and again we would see that we have this symmetry. So in a way, what's happening on the right is just kind of a shortcut, right? So this is a way to think about it conceptually, but north and south poles are just something that we've named, and it has to do with what the magnetic field looks like. The true way to do it, to really think about what's happening, is to think about your current leading to your magnetic field, leading to forces, where that's also going to take currents into account. So this is the exact way to do it, where the physics reasoning really is, but then this is a shorthand that works.